as essentials from the first talk. First, you've just got to be slick with differentiation. If you're not, of course, there's Pemberton and Rao and lots of other books where you can acquire that technique. I put a few revision slides up as well. Second point might be a new one, quite important. What I say that units are important. So what units does dy by dx come in? And the answer is the same as y divided by x. So that's a nice, simple result. The third thing, the small increment formula, tells us how you can take information about a function at a point, its value and its slope, to work out the value at nearby points, to get an approximation to the value of f of a plus h. That seems quite... That doesn't sound too exciting to start with, but we'll see it has exciting applications. Next point is simply about what marginal means in economics, and it means, so C prime of Q means dC by dQ. That's marginal cost. And there's a distinction which I keep emphasizing. You might have been told that marginal cost is the cost of an extra unit, but that's not quite true. So I would not like you not to say that any longer. You can say it's roughly the cost of an additional unit. But we must make that distinction between dC by dQ and C of Q plus 1 minus C of Q. They would be the same if the small increment formula were an exact formula, but it's only an approximation. I'm going to go straight back to chat immediately to see whether everything's going okay. Okay. Are the skills sessions continuing all term? Yes, they are. Every week. On Canvas, you have to sign up for workshops. Are they the same thing? I think this was something Joanne arranged. Just at the moment, you can sign up, but it has no effect because you can, I believe you can come in any case. Later, that might change. We might impose a limit of 100 on each of the 3 sessions. But I'm not doing that at the moment. I just want to be sure that everyone can attend everything. Zheyuan, why is log of 0 negative infinity? Well, there's a lot. When you say why, I could answer it in different ways. I shan't go into it in detail, but if you draw a diagram of the logarithm curve, you'll see that as x tends towards 0, the logarithm shoots off towards minus infinity. I could give you other answers, but that would hold up the session at the moment. Perhaps it's something we could discuss privately. And Harrison, where should you learn about Taylor series if you don't know about it? Well, I'm not teaching Taylor series this year. It's something I hope some of you have done at A level. You can find out more about it in Pemberton and Rao, for instance. If it's not doesn't turn up there, let me know. But it's one of these fundamental calculus topics. I'm sure Pemberton and Rao would talk about it. But for this term, the small increment formula, which is one step on the way to Taylor, is all that we'll need. I'm going back to share screen now. So, for example, the marginal cost of producing ships. So there's the cost function for ships. I'm just checking that it is it an upward sloping curve? I think it will be. I think it will be.
Sub in Q for 20.
We'll come to that in a moment anyway. So what do we mean by the marginal cost? Well, it means dc by dq evaluated at q equals 20. And an abbreviation for dc by dq is c prime of q. And there, c prime names an entirely new function. And we can work out that function. It's 0.2q plus 10 plus 8 over q. So there you are. It's a function. It's not just a value. And that means we can plug in a particular value to it, like 20, and get a numerical answer, which is 14.4. Because this notation here, c prime of 20, is a little bit confusing. If you think that c prime of q means, oh, differentiate c with respect to q, that doesn't work. That's not the right way to think of it. First you differentiate with q, and then you plug in your value of 20. So get your derivative function, and then plug in your value. When you've done that, so the marginal cost is 14.4, but the cost of producing another ship is C21 minus C of 20 is 14.49. Could you make sure you're muted, please? I can hear someone.
好，就这个语气吧。你就是经管一班的王同学吗？是啊，你是？我是你隔壁学校的。其实我偷偷喜欢你好久了。真的吗？你是隔壁学校的，初中还是大学啊？我初中的啦。你不会嫌我小吧？不会，有空一起吃个饭呀。连初中都不放过，看我怎么治你。 这个头像是你本人吗？是呀，怎么啦？你长得挺漂亮的，但是很多人说你真人比照片漂亮。真的吗？那要不现在我们一起出来打游戏？哥哥，我最近迷上修了，要不我们打一把，你赢了我就出来，你输了就答应我一个要求，好不好？好啊，不过事实说明我可是职业战队的打野，可别说我欺负你了。哼，我倒是想看看到底谁欺负谁，给我跪下！ K， 你一定要帮帮我，我被渣男欺负了。那个渣男因为王者打得好，在学校里玩弄女生感情。K， 你一定要帮我治他他。我回来了，我是城镇的王者。
I'm looking. Oh yes, here we are.
玩家，全国没有几个男玩家甚至职业选手能打得过我，拥有各路国服、无数金海的英雄。你们知道吗？城镇的那个最强今天。
Right, sorry about that. Now this point's about the unit of dy by dx. The take-home message is that they're the same as the units as y over x. And if you just want to memorize that fact and aren't interested in the explanation, that's fine. Student Q at the bottom of the screen explains in rather large detail, and that's a good explanation. But if I'm going to put it a little bit more simply, I would say that dy by dx, of course, measures slope. And how would you measure a slope in general? It's the amount of y you get for a certain amount of x. And the amount of y you get is measured in y units. The amount of x you get is measured in x units. So it makes sense that the derivative has the same units as a common or garden slope. That's the way I would express those ideas. But it's the first point that's important. Y over x has the same measures as y over x. Here's a quiz question, and the score was 79%. I'll just let you read the question. So what's happening? We've got a a value of 10. I beg your pardon. We've got a function. We're asked to evaluate it at a value 10. We're given the slope there and asked for the value at a nearby point. Right, I've got a new technology here. Let me see whether it works. And I'm hoping to show you this on my whiteboard. So is this going to be visible for you? So we've got a function. Can you see that? I might have to close my curtains. Is that any better? A bit better, maybe. I mark a point on it. I think this is 10 in the example, but it's called A in general. And we have a function. This is f of x. Right, and we know all about the function just here. We know that the height is f of a. And we're asked to evaluate the function at another point. Let's say this is the point a plus h. Now, one way to do that, if you're calculus orientated, is, and I'm just looking for a straight edge. Okay, so if you're Isaac Newton or Leibniz or someone who knows all about calculus, you say, what's the approximation would I have at that point? And they would join a tangent, straight line approximation, and they would say, well, if we know the slope at this curve at this point, and we know our increment, we can work out a good approximation to this. This is the true value. This is what you're looking for. But without full information about f, this is the best you can do. That is, in essence, the small increment approximation. Right, so that's my attempted new up-to-date technology. How well does that work? Is that visible? Excellent. So that's what we're doing. You won't be able to see the diagram as well, but that's the idea. My A is the value 10. What about, we're asked to guess the value at 0.1. So that 0.1 will be the h, the additional h value. Usually taken to be small, because the smaller it is, the better the approximation works. What you need then is the slope of the curve at 10. We tell that's -3, and then the small increment formula will give us our approximation. So I'm not going to take it further, because I believe it's a question on the quiz, certainly on a previous quiz, and I hope it won't give too much trouble, because 80% got it correct last time, or when I set it in a quiz. Here's a rule you use from differentiation. Again, I hope it's something you've learned at A level. it's the rule for differentiating a function of a function, like f of y of x. It's sometimes called the chain rule, but what I call the chain rule we'll discuss in week 4 probably. So a function of a function is something unpleasant looking like the square root of log of x. And clearly student Q's been helping me write these notes because they've said, well, that's only going to make sense if log of x is non-negative or positive. And for that to happen, x has got to exceed 1. So we'll put that in. And if you'll be impressing the markers if you notice areas where a function is valid, where it isn't. How do we apply this formula? Well, let is a great word to make clear what you're doing. So let f of y be the square root of y. And then what about y itself? Let y equal log of x. Then you've got the two things you need to use this formula. And the answer is, as I have here, it's the answer in a sense, but it would be better to express it just in terms of a single variable. So now we'll substitute back in our value of y to get 1 over x times 1 over 2 root log x. And now finally we'll simplify a little bit and get rid of the times sign to get 1 over 2x log x, provided that x is greater than 1. This sort of rule you just have to practice, and I'd recommend using brackets and writing things out explicitly. When we come to discuss the log in a moment, you'll see why. But let me go back to chat for a moment. Group Chaker, group 8 for the seminars says that it's 1 a.m. That's not correct. Thank you. I'll correct that later. Harrison, Taylor series weren't in A-level maths, only further maths. Will it hold you back if you don't know about it? Well, it's not for this course, but it would just be something that would be good for you to learn about when you've got time. If not, it'll probably come into maths methods in your second year course. Amy, do you need to sign up for the small group seminars at the beginning of every week? Or do you keep to the same group? As things stand, I think you keep to the same group. But clearly the classes are in a mess, so clearly there are going to be more announcements about them. So just please stay tuned. Jack, you've told me I can mute everyone. Thank you very much. That would be useful. Just checking how to do that. Okay, that's something I can't quite see how to do at the moment, but I'll try to master it. Karanjit, when finding the cost of another ship, should we just plug values into CQ for 2 values or differentiate first? No, you want to work out, say, C of 11 minus C of 10. That is the cost of the additional ship. If you differentiate, you'll get the marginal cost, which isn't what the cost of another ship is. The PR book is discussed in the document I I put round the other day. Right. So I gather from what you say that you can actually see that diagram, which is good, because in that case I can use it again. I can use the screen again, I mean. Because this is a very common error. You can, while you read what it says, I'll clean my board. Right, so it seems to make sense. If you differentiate log x, you get 1 over x. So surely, if you differentiate log of 4x, you should get 1 over 4x. But I'm afraid it's not so simple. Because you're not differentiating. It would be true if you were differentiating log 4x with respect to 4x, but you're actually differentiating with respect to x. So there's a different answer. And above is how it's done systematically. It's a function of a function. So let y of x equal 4x. And then if you do that, you get dy by dx is 4. Let f of y equal log y, well, and then differentiate df by dy is 1 over y. Y is 4x. So you can see what's happening now, that because of this dy by dx factor of 4, you get cancellation. And the answer is just 1 over x. So to be on your guard about that, that's a common error. Here's another method of getting the same answer, and it's to use the most important property of logarithms, namely that log of ab is log a plus log b. So if you apply that to 4x, you get log 4 plus log x. But log 4 is just a number, pure number, it's about 1.4. And when you differentiate, therefore, it vanishes. And that's why the answer is just 1 over x. It's not 1 over 4x. And whatever value you put up here, a trillion or something, log of a trillion x differentiated with respect to x is just 1 over x. The challenge is, well, I meant it originally as a challenge to you, but since I can now I've got my whiteboard up and running, perhaps I can make it a challenge to me. Let's see if we can explain that, why that is. So we've got an axis. We've got our nice logarithm curve. So this is the x-axis. We've got our logarithm function going up like this. This is log of x. And now what happens if we put in log of, let's say, 4x? That's equal to log 4 plus log x. So that means that I should be writing ln, shouldn't I, this year? I've written log in the past, len. So log 4 is just the constant, that's 1.4 we decided. So all that taking log of 4x does, as opposed to log x, is just simply to kind of raise that function a bit so it looks like this. It's simply an upward shift. There's no change of shape or anything. And that means that if you evaluate the slope at a particular point here, it'll be exactly the same as the slope at the distance log 4 above all the way along. So that's what the result means. I hope that was visible. Jack says, I click on Manage Participants. Brilliant. So thank you very much, which I'll be trying to do in the office period I conduct this afternoon. Let's see whether I've mastered it by then. A quiz question. And again, it's a slightly more complicated function. Student Q would probably tell me to work out where 3 cos 4x was positive and impose that as a limit, which is true. That's what I would do if I was really being careful and minding my mathematical manners. So this got 65%. And I think just because probably it's a slightly complicated function. I can imagine the 3 going missing or something like that. But to make this, if you're not sure how to do this, first of all, use your important logarithm multiplication addition rule. So if you can make things simple, makes things simpler for yourself, of course, do. And that means if we do that, we won't have to worry about the 3 because it's log 3 is a constant. It's slightly greater than 1. Differentiating, it's 0. And the answer will be the same as log of the derivative of a log of cos of 4x. And then I'm not answering the question for you, but just advising you how to proceed systematically. What's your y function? What's your x function? Well, I beg your pardon, what's your f function? And we apply the same sort of ideas as we did slightly earlier. Right, the next bit, like there are probably other things in the course like this. I like them. I put in because I like them, and I think they will interest some of you. But I can imagine they might intimidate other people. So you don't get intimidated. There's enough non-intimidating material in the course. This isn't the sort of thing I would set in an exam. But I think it's an attractive application of the small increment formula. Right, so student Q is always keen for knowledge. I said that the SIF can be used to get many basic differentiation formula. So student Q set me this as a challenge. The derivative of FG is F prime G plus FG prime. Why is that? Well, like a lot of answers, it starts from a definition. How is F of G prime defined? And the answer is, so if you think of FG itself as as an entirely new function, you evaluate that function at x plus h, and you get f of x plus h times g of x plus h. And then you subtract its value at x, which is f of x times g of x. Right, so where can we go from here? Well, we've got the small increment formula. And that allows us to express f of x plus h and g of x plus h in another way. I've got this formula for f of x plus h, this approximate formula. It's approximate, but the smaller h gets, the more accurate it'll get. That's the great thing about the small increment formula. The smaller h gets, the more accurate it becomes. So we can use the small increment formula on both f and g up here. When we do that, we'll get a very long expression. So to keep things simple, I'll still write f of x plus h, but whenever I have anything that just depends on x, like f of x, I'll simply write f. Or f prime of x, I'll simply write f prime. So that'll cut down the amount of ink. Let's do that up here. All right, here's the formula we start from. Here are two applications of the SIF. So plug those two into the formula at the top of the screen. And well, first of all, plug those two formulae into the first term up here, and then subtract FG. And everything simplifies down to this expression. So I'm not going to talk you all the way through that. That's something I hope you can do yourself with pencil and paper. So that's what we get using the small increment approximation. But now we're asked to push h towards 0. That's what it says up here. The limit as h tends towards 0. Well, if you do that, of course, the second term vanishes. And you're left with the familiar rule for differentiating a product, which the great Leibniz got wrong. He thought it was f prime times g prime to start with. So calculus wasn't easy to start with, but it's got easier down the years as we've focused more and more on it. Revenge of the SIF, but don't worry, I'm not going to go all the way through this. If you really fancy yourself as a student Q or a hot shot, you can try those techniques to obtain the composite function rule. Okay, so, but if you can't do that, don't worry. It's not part of the course. I'll give you some hints. Start from the definition. The definition involves y of x plus h. You can use the small increment formula on that. And then when you do that, you'll get f of this bit. But this bit includes another small increment. It's not h itself, but it's h times y prime. So call that k, and then see how far you get. That's a very quick explanation, but then student Q or student super Q are very quick to understand. Just as I say, just for fun. And that will be the end of talk 1. So that's a good moment to go back to any questions you have. How far have we got? Right, thanks for letting me know that you could see the board okay. I wasn't quite sure. Yeah, Manpreet, there's something about the PR book in general course information. Group 8 seminar was at 10. Has it moved to 1 p.m.? No seminars have moved. If it now says 1 p.m., that's a mistake. It's actually a mistake I've made. So I'm very sorry about that. I'll check that after the session. How would differentiation be applied in an economic scenario? Well, we'll see plenty of examples. One example we've already seen would be to obtain the marginal cost. But there'll be lots of other marginals as we go along. If you don't understand some of the maths we've just been through, where should we look? Well, I wouldn't expect you to understand it all now, because you're still in the passive learning part of the process. The next step is to start solving problems. And when you get stuck on those, then you go to the textbook and perhaps back to the course notes and ask other people. It's a big interactive process, which I'm starting the ball rolling, but the other activities are where you will really do your learning. Will I put these slides onto Canvas for you to look at? Yes, they're already there. I keep updating them, and when I update them, I put the new version onto Canvas. Best place to find lots of practice questions. Well, if you look around, there's plenty of on Canvas. There's some within the course notes themselves. There are examples I give and then solve. Then there are the separate problems and solutions. There are the quizzes, there's Pemberton and Rao. I'll probably put up the examples I do in the skills lectures. I'll probably put up some old exam questions. So I don't think you'll be short of examples. Okay, thank you. That was all about differentiation itself. Talk 2 was about 2 variants on differentiation. One is growth, and that's where we're particularly interested in growth. We're interested in dy by dt, but we want, as it were, not absolute growth like you get in a simple interest rate, but proportionate growth as we get in a rate that's compounded. And these are my essentials. First of all, simply how the growth rate is defined. Okay. And it's difference from rate of increase. And then Marshall's elasticities, which are dear to the heart of economists, and how they should be interpreted. And this material is largely practice. So I want you to understand the basic maths, but then it's clearly something you should just get very familiar with through solving examples. A growth rate is... wait a minute. I shall try apply Jack's method now, and... I think we're okay, sorry. That's how the growth rate of A is defined. A hat is defined this way. And that will actually work for negative A, but we normally think of it as applying when A is positive. Sometimes written in terms of this Newtonian dot as A dot divided by A. So always start with some examples. If, suppose A of t equals t squared, and then if you imagine the graph of that, it's a parabola quickly curving upward. And that means that the slope is increasing as t increases. So you'd normally say that's a very fast growing curve. But actually its growth rate is 2 over t, dt squared by dt divided by a, which is t squared, 2 over t. And as t gets large, the growth rate becomes very small, which seems counterintuitive. But as we'll see, constant growth means exponential growth, which is faster than t squared. That explains that explains this result. Although t squared seems to be a fast increasing function, compared with the exponential function, it isn't. That's why you get this surprising result to start with. What has a what's the simplest function from a growth point of view? it's the exponential functions. Something, an asset attracting a fixed rate of interest will grow at a constant rate. Won't increase at a constant rate, but it'll grow at a constant rate. Here's an example. Or of course, a virus infection in an infinite population. If everyone who gets it infects a certain number of other people, greater than one, in a certain length of time, you'll get exponential growth. It has to end somewhere, if only because the population is finite. So functions of this type, 100x of 0.2t, have a simple growth rate. Comes out as 0.2, and our measure has shown that. This term exponential growth you hear on the radio a lot. I'm never quite sure what people mean, because unless they're all good mathematicians, I don't think they mean this. I think they probably mean just faster than proportionate growth, or faster than constant growth. Perhaps they mean that if they graphed the function, it would curve upward. So in our terms, it would just mean convex. But if you're talking to a mathematician, they would say, well, what's meant is something that grows at least as fast as the exponential function. And there's actually a useful result which says that all exponential functions will eventually beat all power functions or polynomial functions. So if you make alpha to be an absolutely tiny number and n to be an absolutely huge number, nonetheless, there's some value of t at which the left-hand side will overtake the right-hand function. If you graph the two functions, they will eventually cross, and the exponential function will win. That's quite a useful function, a useful idea. I shan't try and prove just now. So I'm not sure what's so wonderful. What I had in mind when I wrote this screen, it doesn't look all that wonderful. All it says is if we replace 100 by any parameter and 0.2 by any parameter, including a negative one, you'll get constant growth, and the growth will come out as rho. So whatever you have here, 0.2, will translate into the growth rate. Exercise, draw sketch graphs of these two cases. I could draw them, but I think you can do that yourself. So in the second case, constant decay is the graph of, like the graph having the same shape as e to the minus x. This comes up a lot, so you should be familiar with that graph. It just curves from some point on the y-axis, curves down towards the x-axis, but never quite hits it. There's an alternative formula. It's if you're good at differentiating of a function, you can see that straight away, I hope, that this is true. So that this is just an application of the rule for differentiating a composite function, log of a of t. Because if you differentiate log a with respect to a, you get 1 over a. But then there's another factor that comes from differentiating a with respect to t, and that's dA by dt. And we do it here using both methods. calculate the growth rate of 2t cubed, and it comes out as 3 over t. And especially if suppose a is defined in terms of the exponential function, then log undoes exp, so that's going to lead to a very quick and useful simplification. Yining, you want to know how to express f prime of a times h on a graph. Right, let's see if I can do that. Using this, I'll put it up here again. So along here we have x. Here we have our function f of x. Here we've got our point A. Here's our h. And this is our height f of a. Now this is a straight line. So this will have some equation y equals mx plus c. The m will be the slope, which is f prime of a. So this thing is equal to, I'm not sure, I hope you can still see it, equals, I'll write it up here actually, y equals f prime of a times x plus c. Well, I'll set it as a little challenge to you. If you put this thing, your answer will be what this thing is. C will be, as ever, I'm not getting, this is getting too complicated for me, I admit. I'll look through it afterwards, but this is the height f of a plus h, and you're going to use that. So it will be the height times, it'll be this distance times the slope, which I think will give you this extra increment here. If I seem to know not exactly be secure with what I'm doing, that just shows you that I'm not all that fast either. But I think that's the answer. I'll put you as a challenge to you to try and work out exactly what that equation is. I hope everything can be done in terms of trigonometry. Okay, so if that's undermined your faith in me, that's good, because it'll make you a bit more self-reliant. Sandeep, could I back up to the growth definition, please? I won't do that now if you don't mind, Sandeep, because I want to move on, but it's the growth rate. If y depends on t, then the growth rate of y is y hat divided by y. I beg your pardon, it's y dot divided by y. 1 over y times dy by dt. Zhe Yuan is, I guess you're asking about this dot. Is a with a dot on top the derivative of a with respect to t? Yes, it is. Yuan, if you're on top of everything, do you need to use Pemberton and Rao? No, just do things that actually help you. If you're interested in what's in Pemberton and Rao, by all means, have a look through, see if there's anything you want to pursue further. But Joshua, constant growth. Yeah, for constant growth is basically the growth of an exponential function. The derivative of an exponential function is itself. So you divide the derivative by the function. They're the same thing, so they cancel, and that's the way you get a constant. Okay, thank you. And you can check yourselves at some point. I won't ask you to do it now, that you can use the result we've just put up, this one, to obtain the other things we've already obtained. And you'll need to know the main rules about the log function, including how to differentiate it. And by both methods, this is where I think the material starts to become quite attractive. You get what I think is a really nice looking rule like this one. It really says that growth inherits the nicest property of the logarithm function. The growth of x times y is the sum of the two growths. The growth of x divided by y is the difference. And we've just got to be a little bit careful about y not becoming 0. What about the growth rate of t to the 7th? Then the growth will be 7 over t. But you can't assume that everything's going to be simple. Student Y thinks that the growth of y plus z will be the sum of the two growth rates. But we're suspicious of that because we've just seen that the growth of y times z is actually the sum of the two. So what goes wrong? The student Y does tend to make these extravagant guesses just to make things simple. Would tend to assume that the square root of a plus b is the square root of a plus the square root of b. That's not true. There are cases where it's true, no doubt, perhaps if b is 0, but in general it's not true. So if you don't want to be student Y, you've got to be a bit more systematic. What do we mean by the growth of y plus z? Well, here's the definition. The definitions will always give you a start in an exam, nearly always. If you don't get any further, you'll get some marks. But once you've written the definition down, that will probably tell you where to go next. How can we make progress? Well, we can differentiate y plus z, because the derivative of a sum is just the sum of the derivatives. So we get y dot plus z dot divided by y plus z. But we'd like to get that into, that's correct, but let's get it in terms of growths. We can use a little trick here. There's a sort type that often comes up. If y hat is y dot over y, then just multiply both sides by y, and you get y dot is y times y hat. And we can plug these two expressions in up here. This is the sort of thing you only get from lots of practice. Put those two expressions up here, and you've got an answer in terms of the growths. I would probably take things a little bit further. What we're assuming, are we, that y and z are positive? No, well, let's assume it anyway. Let's assume they're positive. In that case, y divided by y plus z is a number between 0 and 1. Again, forms like that are often coming up, and it's often useful to notice that they are between 0 and 1. So we've got the growth of y plus z as a weighted average of the two individual growths. Again, this is not a result that's important for the course. It's not something I want to teach you, as it were. I'm just illustrating what you can get from the methods we're learning. So we can conclude from that form that the growth of y plus z is somewhere, it's a weighted average, or what later on we might learn to call a convex combination of y hat and z hat. A weighted average will do for now. And a weighted average of two numbers will lie somewhere between them. But the weights will vary as time varies. And then elasticities. How are they defined? You take a derivative, dy by dx, and turn it into something unit-free by multiplying by x over y. For the formula to make sense, if we're allowed to be a little bit mystical and work in terms of what these actually are differentials, dy and dx, if you think of d as meaning a small change in y divided by a small change in x divided by x. And that would, if you're allowed to write down formulae like that and manipulate them, you'll get what we have up here. What's the interpretation? Well, suppose if it comes out as -10, what it's saying is that a 1% increase in x leads approximately to a 10% fall in y. That word approximate there is needed. If we replace 1% by 0.1%, then the fall in y would be approximately 1%, but the approximation gets better and better because it's based on the small increment formula. The better and better, the smaller the percentage increase. And here's something that has struck me from marking exams. Right, suppose I ask you to calculate an elasticity. You go ahead and do that, and for example, what's the elasticity of cost with respect to quantity? Well, you go ahead and do that, and you do it all correctly. You work out the derivative function, you multiply by Q over C, and you get this expression. And it's correct. But won't get full marks because it can be simplified. And in all these elasticity questions, you've got a y and an x, but remember you've also got y in terms of x. You're given that. So we've got C in terms of Q. We can substitute that in, and then everything will cancel, and you get 1.7. So just remember this as something you often do with elasticities. It's almost routine that you've got that substitution in at the end. Let's just review the three simple cases we've got. Simple for differentiation are things that have a slope that is a straight line. So things of the form mx plus c or a plus bx. So the derivative doesn't vary when x varies. Simplest functions from the growth point of view are the exponential functions. And the simplest functions from the elasticity point of view are what are called power functions, where alpha is a parameter, is a power of x. And then several of our examples show the elasticity doesn't change as x changes. So if you have those in your mind, especially the second two, they come up again and again, and will help you keep things simple. Help you solve things in a simple way if you spot when a case is simple. How are we doing for questions? No more questions. Brilliant. Okay. For instance, this question from quiz 1. Find elasticity with respect to price. Well, this is one of the simple functions I was talking about, because 1,000 over p squared can be written as 1,000 times p to the minus 2. So that's a sort of power. It's the to the power minus 2. And that means the answer is going to be pretty simple. So on the screen, there are some hints about how you might do that. I'm going to leave that to you, but right at the end, if you substitute in your value for Q up here, you will get an orgy of cancellation and a nice simple result. Again, in the past, this question's only scored 52%. But between you and me, it's again a rather simple case. It's the 10 times, 10 divided by the square root of p. But the square root of p is p to the half. And 10 divided by 1 divided by the square root of p is p to the minus a half. So I've given you some pretty broad hints here. Otherwise, you can use the ones on the screen. Here, there are a number of other elasticities you should try, and remember the maneuver. When you've got y in your formula at the end, you can always put in your definition of y in terms of x, and you will usually get further simplification. There's a general result at the bottom of the screen, which probably student Q will go straight towards that. If y is b times x to the alpha, then it doesn't really matter what b is, the elasticity will be alpha. And here are some more examples. So you try those out for yourself. Let's see if there are any that are particularly eye-catching. What catches my eye most probably is the one at the bottom. So y is a simple straight line function. You might expect it to have a simple elasticity, but it's only simple from the point of view of differentiation and increase. It's not quite so simple from the point of view of proportionate change. And that's why the formula does not come out to be simple. Well, someone asked for economics earlier. Here's the closest we'll get probably to a bit of economics here. And it launches us into an area that's actually been genuinely controversial. So we have a government that decides to impose a sales tax, a purchase tax on the purchase of a cow. It imposes a certain amount T. Of course, they're doing that to raise money, to raise tax revenue, called R of T. And we've got a formula for R of T. And you're now all you've got into the habit of visualizing things. So you can visualize the graph of R. It's a quadratic. When T is naught, it'll be naught. If you impose no tax, you won't get any revenue, of course. If you impose a tax, it'll go up for a bit. Then ultimately, the T squared term will dominate and it will start to come down again. So we've got one of the two possible shapes for a quadratic. They can either curve upward or curve downwards. We've got a downward bending curve. It goes up for a while, reaches a peak, and then comes down. Right, so much for reading the question. What's the question say? Find the marginal revenue with respect to tax. Well, that's a pretty straightforward. When the tax rate is 9 golden sovereigns per cow. Well, everyone could differentiate. They got 30 minus 40, plug in your value of 9. The answer is minus 6. Okay. Second part is to interpret what you've done. You've got minus 6, but what does it mean? The Ministry of Finance has hired you. He or she is staring at you vacantly. You now have to earn your money by expressing that in a way they can understand. Well, it's a marginal change, so it means an increase of 1 in T leads to an approximate fall of 6 in R. But what is R? R is measured not in sovereigns, but in million golden sovereigns. So if T's raised by 1, tax revenue will fall by about 6 million golden sovereigns. And that's because, of course, there are a lot of cows to raise tax on. So most students omitted those words per cow. Third part, what's the elasticity of revenue with respect to tax? We work through the algebra here. We get, again, a nice simplification, and the answer is minus a half. Even if you know a value like T, don't plug it into your algebra too soon. You probably find you have to carry a complicated expression, a numerical expression too far down the page. You get more insight if you don't substitute in too soon. So it's minus a half. Explain for the result for the Minister of Finance, the final result. It means that, so what's this minus a half mean? It means 1% increase in the tax rate will lead to an approximately 0.5% fall in tax revenue. And so students tend to do well on A and C, not so well on B and D. quite often this happens when I ask for interpretations. Everyone is so maths focused. They tend to under stress the need to understand what it means. And that leads me on to the controversial economics I've mentioned. So in the example we've seen, we've increased the tax rate, but nonetheless got a fall in tax revenue. Could that ever happen in reality? Yes, it can. Because, for instance, when you impose a purchase tax, you're dissuading people from your revenue. So there's two competing factors: more revenue per purchase, but fewer purchases, and the overall effect is ambiguous. Another good economic word, it has an ambiguous effect. Could go either way. This was stressed in the Reagan era by an economist called Laffer, who said he put it the other way. He said we actually might raise more tax revenue by reducing taxes, and the incoming government was actually keen to reduce taxes and to have a justification for doing so. So it sounds as if it could be everything a government wants. They cut taxes, but they nonetheless get more money to spend. Could happen. And Laffer was himself challenged to explain this at a dinner party, I think, and he sketched his Laffer curve on a napkin and showed how it could happen. You can read about the Laffer curve, about which there was a huge controversy, and it did play its part in policy, but I shan't attempt to summarize that, but it's an interesting topic. Here's a quiz question that's certainly given a lot of difficulty. The average mark ended up at about 65%. I think in other years, before I gave less help, it was less impressive. The world's round, exactly round. Its radius is r meters. I'm at a height h meters. And you can, if you want to draw that, draw a circle, and then from the center, draw a radius out from the circle, and then from the center of the circle to the circle itself, and extend it by a little bit h. And you get this child who is standing at a height h above the world, which has radius big R. So diagrams are wonderful. We can distort the distances we know about to get something we can actually visualize. Then according to the questions done the next bit for you, it says that if the child wants to know the distance to their horizon, and you would draw a tangent in from the top of the child to the horizon and show that distance is the square root of h squared plus 2hr. We've got Pythagoras. And so an additional challenge is to get that formula. And another additional challenge is to show that if h is much smaller than r, then we have this very good approximation, square root of 2hr. So what's the question? Child visits the seaside every year. She's got 10% taller in the last year. So in percentage terms, how much further can she now see to the horizon? It's an elasticity question. You can actually do it by plugging values into the formula, but it's not quite so much fun. So there are my two student Q challenges, student Q and student super Q. The student Q requires a bit of geometry. Student super Q will require a bit more ingenuity. Getting back to differentiation, the reason I put it in is because it's a question I can remember us asking each other at A level when we were learning about differentiation. I don't know. I certainly didn't know what the answer was there. No doubt I had clever friends who could do it. But the challenge is to find the derivative of x to the x. And I'll give you a little bit of help. It's that to do it, you have to know what's meant by x to the x when x isn't necessarily an integer. And the definition is this one. Well, a to the b is x of b times log a. So x to the x is x of x times log x. And if you use the composite function rule and probably the quotient of the product rule at the same time, you might be able to get the answer. The answer's at the end of the slides. There's another way of doing it here, using growth rates. We could remember we decided earlier we could write a derivative as a product of y times its growth rate. If we do that, we can get simplification of this expression and use that. So do it both ways if you're a student Q. Student super Q, who's a bit of a pain in the neck, says, well, of course, that was easy. Let's do the derivative of x to the x to the x. You'll find half an answer at the end of these slides. I described the method, but decided I couldn't face trying to decide whether I was actually pushing it through to a correct conclusion. But I think I know the method. Here ends skills 2, except I should go back and see whether you've got some questions. Jack, exp is just e to the x, isn't it? Yes, we've got those two different notations. The explanation I gave last time is that exp of something is better when it's printed because you can see the exponent more easily. So journals tend to like it. Would the 1.7 on the elasticity question be a percent? Do you know, Joshua, I can't actually remember which question you're referring to now. Don't know, sorry, but I'll check that later. Susan, when you encounter elasticities, should you always assume the initial change was 1%? No, it's when you calculate elasticity, you'll use a derivative, dy by dx, and then times y over x. If you're asked to explain and interpret that, you'll say, well, the elasticity tells you the percentage change in y if the change in x was approximately 1%. That's where your 1% comes in. So I'm not sure now just which question you're referring to, so perhaps I'll leave that. Patrick, the common maneuver for elasticities. Again, we're running a bit short of time, so look at it on the slides. Common maneuver. Basically you work out your elasticity for y, the elasticity of y with respect to x, and then right at the end of the calculation, use the fact that you have a formula for y in terms of x, and that will give you more simplification. Karanjit, how will I conduct office hours this week? Right, so far I've only scheduled one, which is today at 1 o'clock. I put an announcement about that on Canvas. If you want to come, you don't have to, send me an email and I will arrange, I'll try to meet people in the order in which I get the emails. It's a bit crude, but we'll do that for now. And then I'll fix another office period later in the week. Zara, if you can't come to the interactive online workshops because of clashes, could you please just send me an email and we'll sort it out from there. Right. Okay, so it's nearly 11:30. If there are any more questions, otherwise I shall say thank you very much and I'll finish off at past.